Hello, and welcome. In this video, we will explore advanced techniques for integration, which are essential for the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to, first, integrate functions using the method of partial fractions. Second, master the technique of integration by substitution. And third, apply trigonometric substitutions to solve complex integrals. These methods will equip you to tackle a wide range of integration problems, including those found in IB-style assessments. Let's begin. Our first technique is integration by partial fractions. This method is used to integrate rational functions, which are functions that can be written as a fraction of two polynomials. The core idea is to decompose a complex rational function into a sum of simpler fractions, called partial fractions, which are much easier to integrate. Let's work through an example to see how this is done. We'll find the integral of 7x minus 1 divided by 2x squared minus x minus 1. First, we need to factor the denominator. The quadratic 2x squared minus x minus 1 factors into the product of two linear terms, 2x plus 1 and x minus 1. Next, we set up the partial fraction decomposition. Since we have two distinct linear factors in the denominator, we can write the original fraction as the sum of two new fractions, each with a constant numerator a and b over one of the factors. To find the values of a and b, we multiply both sides of the equation by the common denominator, 2x plus 1 times x minus 1. This clears the denominators, leaving us with the equation 7x minus 1 equals a times x minus 1 plus b times 2x plus 1. A clever way to find a and b is to choose values for x that make one of the terms 0. Let's try x equals 1. Substituting x equals 1 into our equation gives 7 times 1 minus 1 on the left, and a times 1 minus 1 plus b times 2 times 1 plus 1 on the right. This simplifies to 6 equals 3b, which means b must be 2. Now let's find a by choosing x equals negative 1/2. Plugging in x equals negative 1/2 gives 7 times negative 1/2 minus 1 on the left, and a times negative 1/2 minus 1 plus b times 2 times negative 1/2 plus 1 on the right. This simplifies to negative 9/2 equals negative 3/2. A, which means a must be 3. So we found our partial fraction decomposition. The original integral can now be rewritten as the integral of 3 over 2x plus 1 plus 2 over x minus 1. We can integrate each term separately. The integral of 3 over 2x plus 1 is 3/2 times the natural log of the absolute value of 2x plus 1. The integral of 2 over x minus 1 is 2 times the natural log of the absolute value of x minus 1. Don't forget the constant of integration, c. And that's our final answer. We have successfully integrated a rational function by first decomposing it into partial fractions. This process is a powerful tool for solving a specific class of integrals. Now let's move on to our second major technique, integration by substitution. This method is essentially the reverse of the chain rule for differentiation. The goal of substitution is to simplify a complex integral by replacing a part of the expression with a new variable, u. This transforms the integral into a simpler form that we already know how to solve. Let's consider the integral of x squared plus 3x, all raised to the power of 4 times 2x plus 3. Notice that the expression 2x plus 3 is the derivative of the inner function, x squared plus 3x. This is a key indicator that substitution will work. We'll make the substitution u equals x squared plus 3x. Then we find the derivative of u with respect to x, which is du dec equals 2x plus 3. Rearranging this, we get du equals 2x plus 3, geeks. Now we can rewrite our entire integral in terms of u. The term x squared plus 3x becomes u, so we have u to the power of 4. The term 2x plus 3 dx is exactly du. Our integral is now simply the integral of u to the power of 4 with respect to u. This is a basic power rule integral. The integral of u to the 4 is u to the 5 over 5, plus our constant of integration, c. Finally, we must substitute back our original expression for u. So the answer is 1/5 times x squared plus 3x to the power of 5 plus c. It's crucial to return to the original variable x in your final answer. This method is incredibly versatile. The key is to identify a part of the integral whose derivative is also present, or can be easily manipulated to be present in the integral. Let's look at another example of substitution, this time involving trigonometric functions. We'll find the integral of cosine cubed x times sine x. Again, we look for a function and its derivative. The derivative of cosine x is negative sine x. Since we have a sine x term, this suggests a substitution. Let's set u equal to cosine x. Then do dx is negative sine x, which means do equals negative sine x dx. Now we substitute. Cosine x becomes u, so cosine cubed x is u cubed. Sin x dx is negative do. Our integral becomes the integral of u cubed times negative do. We can pull the negative sign out. The integral of u cubed is u to the 4 over 4. So we have negative u to the 4 over 4 plus c. Substituting back u equals cosine x. Our final answer is negative 1/4 cosine to the power of 4 of x plus c. This example highlights the importance of recognizing derivative pairs within the integral. With practice, you'll become adept at spotting the right substitution. A very useful result that often arises from substitution is the integral of a function's derivative over the function itself. Consider the integral of fp o f prime of x divided by f of x. If we let u equal f of x, then do is f prime of x dx. The integral becomes the integral of 1 over u do, which is the natural log of the absolute value of u. Substituting back, we get the natural log of the absolute value of f of x plus c. This is a pattern you should learn to recognize. Let's apply it to an example. Let's find the integral of cosine x over sine x. This is, of course, the integral of tan x. Here, our function f of x is sine x, and its derivative f prime of x is cosine x. The integral is in the exact form f prime over f. Therefore, we can immediately write the answer as the natural log of the absolute value of sine x plus c. This shortcut can save a lot of time. Sometimes, a direct substitution doesn't work, and we need a more advanced technique. This is where trigonometric substitution comes in. Trigonometric substitution is used for integrals containing expressions like the square root of a squared minus x squared, the square root of x squared plus a squared, or the square root of x squared minus a squared. The goal is to use a trigonometric identity to eliminate the square root. Let's focus on the first case, the square root of a squared minus x squared. The key identity here is 1 minus sine squared theta equals cosine squared theta. To make our expression look like this, we substitute x equals a sine a theta. Then dx equals a cosine theta d theta. The term under the square root becomes a squared minus a squared sine squared theta, which simplifies to a squared cosine squared theta. The square root of this is a cosine theta. This substitution successfully removes the square root. Let's see this in action with an example. We'll find the integral of 1 over the square root of 1 minus x plus 2 squared. This integral is in the form 1 over the square root of a squared minus u squared, where a is 1 and u is x plus 2. We'll use the substitution u equals a sine theta, so x plus 2 equals sine theta. Then dx equals cosine theta d theta. Substituting these into the integral, we get the integral of 1 over the square root of 1 minus sine squared theta times cosine theta d theta. The denominator simplifies to cosine theta, which cancels with the cosine theta in the numerator. We are left with the integral of 1 d theta, which is simply theta plus c. Finally, we must express our answer in terms of x. Since x plus 2 equals sine theta, theta is the arcsin of x plus 2. So the final answer is arcsin of x plus 2 plus c. This shows how a trigonometric substitution can transform a seemingly difficult integral into a very straightforward one. Let's look at another type of trigonometric substitution, this time for expressions of the form the square root of x squared minus a squared. For this form, we use the identity secant squared theta minus 1 equals tangent squared theta. The appropriate substitution is x equals a secant theta. This leads to the square root simplifying to a tangent theta. Let's apply this to the integral of the square root of x squared minus 9, all divided by x. Here, a squared is 9, so a is 3. We substitute x equals 3 secant theta. The derivative dx is 3 secant theta tangent theta d theta. Now we substitute everything into the integral. The square root becomes 3 tangent theta. The x in the denominator is 3 secant theta. And dx is 3 secant theta tangent theta d theta. After canceling terms, we are left with the integral of 3 tangent squared theta d theta. We can't integrate tangent squared directly, but we can use the identity tangent squared theta equals secant squared theta minus 1. The integral of 3 secant squared theta minus 3 is 3 tangent theta minus 3 theta plus c. The final step is to convert back to x. We started with x equals 3 secant theta, so secant theta equals x over 3. We can visualize this with a right-angled triangle. Since secant is hypotenuse over adjacent, the hypotenuse is x and the adjacent side is 3. Using the Pythagorean theorem, the opposite side is the square root of x squared minus 9. From this triangle, tangent theta is opposite over adjacent, which is the square root of x squared minus 9 over 3. And theta is the arcsine of 3 over x. Substituting these back into our answer, we get 3 times the square root of x squared minus 9 over 3, minus 3 times the arcsine of 3 over x plus c. This simplifies to the square root of x squared minus 9, minus 3 arcsine of 3 over x plus c. This example demonstrates the full process of trigonometric substitution, from choosing the substitution to converting the final answer back to the original variable. We have now covered 3 powerful integration techniques: partial fractions, substitution, and trigonometric substitution. Let's recap what we've learned. Partial fractions are for rational functions, breaking them into simpler parts. Substitution is for integrals, where you can spot a function and its derivative. And trigonometric substitution is for integrals involving specific square root forms, using trigonometric identities to simplify them. Mastering these methods is crucial for success in IB Mathematics AAHL. The key is practice, practice, practice. Let's now work through some IB-style practice questions to solidify your understanding. Here's our first practice question. You can pause the video to try it yourself before I go through the solution. Find the integral of 1 over the square root of 4 minus x squared. Let's analyze this integral. It contains the term the square root of 4 minus x squared, which is of the form the square root of a squared minus x squared, where a is 2. This is a classic case for trigonometric substitution. We'll use the substitution x equals 2 sine a theta. This means dx is 2 cosine theta d theta. Now, let's substitute. The denominator becomes the square root of 4 minus 4 sine squared theta, which simplifies to 2 cosine theta. The numerator is dx, which is 2 cosine theta d theta. The 2 cosine theta terms cancel out, leaving us with the integral of 1 d theta. The integral of 1 d theta is theta plus c. To convert back to x, we use our substitution x equals 2 sine theta, which means sine theta equals x over 2. Therefore, theta is the arcsine of x over 2. Our final answer is arcsine of x over 2 plus c. Here is our second practice question. Again, feel free to pause and try it yourself. Find the integral of 2x plus 1 divided by x squared plus x plus 1. Let's look for a substitution. Notice that the numerator, 2x plus 1, is the exact derivative of the denominator, x squared plus x plus 1. This is a perfect candidate for the f prime over f rule. Let's confirm this with a formal substitution. Let u equal the denominator, x squared plus x plus 1. Then du dx is 2x plus 1, so du equals 2x plus 1 dx. Substituting these into the integral, the numerator and dx combine to form du, and the denominator becomes u. We are left with the integral of 1 over u du. The integral of 1 over u is the natural log of the absolute value of u plus c. Substituting back for u, our final answer is the natural log of the absolute value of x squared plus x plus 1 plus c. Let's tackle our third practice question. Take a moment to consider the best approach. Find the integral of 1 over x squared plus 4x plus 5. This is a rational function, but the denominator, x squared plus 4x plus 5, does not factor into linear terms. This means partial fractions won't work. The key here is to complete the square in the denominator. Completing the square, we can rewrite x squared plus 4x plus 5 as x plus 2 squared plus 1. Our integral is now 1 over x plus 2 squared plus 1. This integral is now in a standard form. It resembles the integral of 1 over u squared plus a squared, which is the arctangent integral. Let's use the substitution u equals x plus 2. Then do equals dx. The integral becomes the integral of 1 over u squared plus 1 du. The integral of 1 over u squared plus 1 is the arctangent of u plus c. Substituting back u equals x plus 2. Our final answer is the arctangent of x plus 2 plus c. Let's move on to our fourth practice question, which combines substitution with a trigonometric identity. Find the integral of sine cubed x. When you have an odd power of sine or cosine, the strategy is to split off one factor and use the Pythagorean identity. Here, we'll split off 1 sine x. We can rewrite sine cubed x as sine squared x times sine x. Then, using the identity sine squared x equals 1 minus cosine squared x, the integral becomes the integral of 1 minus cosine squared x times sine x d. Now, this integral is perfectly set up for a substitution. Let u equal cosine x. Then do is negative sine x d dx. This means sine x d is negative do. Substituting, we get the integral of 1 minus u squared times negative do. This simplifies to the integral of u squared minus 1 do. Integrating term by term, we get u cubed over 3 minus u plus c. Substituting back u equals cosine x. Our final answer is 1/3 cosine cubed x minus cosine x plus c. For our final practice question, we'll use the method of partial fractions. Find the integral of x minus 9 divided by x squared minus 2x minus 3. This is a rational function where the degree of the numerator is less than the degree of the denominator. The first step is to factor the denominator. The quadratic x squared minus 2x minus 3 factors into x minus 3 times x plus 1. Next, we set up the partial fraction decomposition. We write the fraction as a over x minus 3 plus b over x plus 1. Multiplying by the common denominator, we get x minus 9 equals a times x plus 1 plus b times x minus 3. To find a, we set x equals 3. This gives 3 minus 9 equals a times 4, so negative 6 equals 4a, and a is negative 3/2. To find b, we set x equals negative 1. This gives negative 1 minus 9 equals b times negative 4, so negative 10 equals negative 4b, and b is 5/2. Now we can rewrite our integral. It becomes the integral of negative 3/2 over x minus 3 plus 5/2 over x plus 1. Integrating each term, we get negative 3/2 times the natural log of the absolute value of x minus 3 plus 5/2 times the natural log of the absolute value of x plus 1 plus c. That concludes our session on advanced integration techniques. We have explored partial fractions, substitution, and trigonometric substitution, and worked through several IB-style examples. Remember, the key to mastering these methods is to practice regularly and to develop an intuition for which technique to apply in different situations. Thank you for watching.